think that you right. So maybe you can okay. Is there any lag? Okay, then I think it is fine. Okay, because I got the answer after a few seconds. It felt as if you heard it a little few seconds late. So I was wondering if there is any lag. Anyways, yeah. So maybe you can share with me what you have read or thought about profinite groups or some example that I gave. Yes, certainly. I mean, yeah, I mean, whatever I know, the definitions, I can get started. Yeah. Okay. So let us see. Mhm. I think the answer should be no. But since I have not studied that area, I do not. But I think the answer should be no. Why? Why did you? What do you think? Huh? Okay. Okay. So let's see. So are all uh, just to understand what you're saying, right? In the question. So your question is: are all simple groups G equal to cal A over Q for some Q for some K uh, galva? And but then when you say that every group is can be built up from simple groups using extensions, group extensions, can you make that more precise? All simple groups can be made up. Right, right. Okay, yeah, that's fine. Yeah. Okay, yeah. So you're basically talking about. Okay, I think I can understand what you're saying. We are talking about composition series and things like that, right? Yes, yeah. Okay, so since that is a different kind of discussion, let's not get into that. But there is a nice theory there also. But yeah, for this actually, yeah, I do not know the answer. But what I can suggest is, why don't you try with some simple groups, maybe a. Right. Yeah. So maybe you should think. So what simple groups would you try? Maybe. Uh, AN, that's right. AN is there, of course. And any other simple groups means more concrete. But that's not, is that finite? That's not means over, or maybe you mean over some finite field. Right. Okay. Yeah, these are there, but if there are some, okay. Yeah. Yeah, maybe this will have small size for small q. Hmm. Yeah, you would have to try some examples because I don't, yeah, don't know this at all. Okay, yeah, try it and then maybe I will also try it. Maybe I should. Yeah, I'll just note it down. S- And even if the group extensions are uh, can be used. Group extensions can also be fairly complicated. So it's not even clear whether solving for simples will solve for all groups, all finite groups. As, and I even for that I don't know the answer. Right. So yeah, these are all very. That's why. So there is a book called Inverse Galois Theory, right? Probably or Galois Theory over Q or something. I think that one of them is by Serre. So you can try to see that. Yeah, it's exciting, but unfortunately, I never thought much about that. Anyways, yeah. So let's move to profinite groups. Vaishnavi, so we are just starting with new topic. See, I mean, it's related to Galois theory. It means I at least I see some there is some relation. What I've read, but let's see. Profinite groups. So there are several ways in which this can be introduced. Maybe so. Let me start. Let me introduce it through a concrete example. Through a concrete example. Okay. Otherwise, that means one can define this as a topological group which is compact and totally disconnected. That is one definition, but I don't know how helpful that definition is. Yeah. So let's understand this through an example. Okay. So, which actually I recently was looking at, so I can do it. Yeah. So fix a prime, fix a prime. Okay, just a prime, not a prime ideal. So fix a prime P in Z, and okay. So consider this product, this be an infinite product. Yeah. And yeah, please interrupt me or anything. It's just yeah, if there is something. Okay. So we look at this infinite product, and from here we pick some special things. So maybe first I should name this. I'll just name this P because this is not going to be very useful. This set is not going to be needed later. So just call it P. But what we will be interested in is this set. And this will be a group, and this is going to be an example of a profinite group. Okay. And through that, maybe we can say the definition. So this will be made up of, this will be a subset. So, yeah, I should start with x1, so on, such that xi is congruent to xi plus 1 modulo p to the I. Okay. So what we are doing basically is, let's say that there is some a in this. Let's say there is an a in this. Then you just take this a modulo p square, right? And it might be 0 modulo p square, right? So you just take it modulo p square, and that's what you write here, right? And then you keep doing it. And this kind of element is what we are storing. was what we are taking in our set. Okay, so this is just a definition. And what do I want to say? Right. I just want to say that look at ZP under addition. Okay, is a group, and the addition is of course pointwise, coordinate wise. Okay, group. Okay, and this is of course um, it's also a ring. Okay, but so far we just look at it as a group. Is a group, and this is called uh, say group of p-adic integers. Okay, a lot of results which we prove for integers can be generalized. Like last time in one of the classes we were discussing Lucas theorem that has a p-adic generalization. But yeah, yeah, if you were not there, it's fine. Yes, but so far, like, what is profinite about all this? So here we will talk about some topology on this group because that's the only way it will become profinite. So, so to put a topology on, because this is the this so far this is quite straightforward. This is also straightforward, but yeah. Okay, topology on ZP. So how is it going to come? So well, in first step, we just first step. Right, you just put the product topology. And before that, what topology do you put on these finite sets? The quotient topology. Right, you can put that. And what is that going to be? That's just going to be the discrete topology. It means it will turn out to be the discrete topology of these finite sets. Right, I suppose because it's a finite set, so the easiest way would be to just say the discrete topology. But yeah, of course, quotient. So you put quotient topology. So if you take Z and you have the discrete topology on Z, and then you put the quotient topology on this quotient, that will turn out to be discrete. Okay. So I will just say discrete topology. So you put discrete topology on finite sets. So now I'm writing it in a way that the features of a profinite group will come out. Okay. So discrete topology on each ZPI said. And then you take, of course, product topology on P, and on ZP we take subspace topology. So these are all natural. These are just words, but this is the natural thing to do. Okay. And this is the topology that we put on this. So yeah, so then set P plus with the topology, let's call that tau. Okay, is this you may need to prove from the axioms of a topological group. This is the topological group. Okay. So now, yes, yes, that's right. So you have to, you should, this is a good exercise to prove this. So now there are two ways one can go, as I see, is one can um, try to show why this is an interesting topology. Does it come from an interesting metric, and so on and so forth. Or one can use this to define profinite groups. Okay, so let me use this to define profinite groups first, and then maybe can talk about the topology. Why is it interesting and so on. Right. So there are some things to be checked, and yes, yes, of course. Vaishnavi, are there any questions? No? Fine. Okay. Right. So what I am going to do now is maybe here only I will erase things and so on. So instead of these, I will just replace these by finite sets. Okay. So I will just replace this by finite sets, finite groups, finite groups. And yeah, here I will, yeah, maybe it was not such a good idea to do this. I'll just write it on the next page. Yeah. So let GI, yeah, this may seem very dry, but then let's just see for some time and then we'll get to maybe more examples. Let GI I in I be finite discrete. Discrete means with discrete topology. Discrete groups. Now something interesting, something slightly new uh, will come. Right? Now I will be a poset. Okay. I be a poset, and right, this something. Then I just means there is just a partial order relation, but I'm just thinking if you need anything more. I think no, but yeah. And here comes the interesting thing. Phi ij, these are maps from gi to gj, where the map is from higher to lower. Okay, so I bigger than j. So by that same partial order. So now this is yes, yes, yeah. That's okay. So do we recognize this in the previous example? These maps in this, which I have destroyed partially, unfortunately, kept it. So do we recognize that? So what was the poset? The poset there was just in natural numbers with the usual ordering, right? And what was yeah, and what were the maps? For example, what was n to n minus 1? What was this map? Right. Yeah. So yeah, and that can be that I just say that A goes to A bar. So it is the natural quotient map, right? Because Z p to the n minus 1 is a quotient of this. So this quotiented by the subgroup p to the n minus 1 Z p to the n minus p to the n. This quotient is basically this thing. So yeah, it's a natural quotient map, but yeah, as Mahima said, it's just taking A and taking it mod p. So that was that map. Those were the maps. And then, of course, if I replace this by M, then also the map was the same. You could say the same, but it's understood. There is one more thing there which I am not saying. It might complicate it. So I'm not saying it right now. Or I don't think I don't think you people will get confused because if I just say it clearly, there should not be any confusion. Yeah, so I'll just say it. These are the maps such that, I mean, as you expect, by there is some consistency. Sorry. So yeah. Okay. That is what was happening in our example also. Right? If you compose uh, taking mod once, mod again, that's the same thing as taking. You understand? Yeah. So this consistency. Now, I'll just give a definition. It has a lot of meaning. It's called inverse limit, and it's very important. But we will not use the properties of it, so we'll not say it like that. I'll just I'll use the notation. So this is my G, and what it means I have not said. So I should actually write it like this, and this is defined as. Now you can guess the definition. So of course, first it's probably needless to write, meaning actually I should have written it outside, but let's write it here. And what should I write here? So basically, uh, Gj is equal to phi ij of Gj of Gi, sorry. Right. So we are taking basically the coherent sequences kind of, which are coherent with respect to these maps. Right. So just an example, if you have this is just a diagram. I shouldn't say this is an example. Just a diagram. So suppose that is 5 and 4, 3, 2, 1. Uh, right? Yes. So now there are maps. And so what we are picking is like maybe if I pick G5, then G5 goes to G4 under that map 5, 4, 5. Sorry, 5, 4. Yes. And maybe this is going to G3 and this is going to whatever under those maps. Then that sequence we will pick, correct? From this collection of all sequences. Right? So this is my collection of all sequences, and now I'm picking the correct. I mean, I'm picking those sequences which travel through these maps. okay, which travel through these 5 eyes. Correct. Perfect. And this construction is called inverse limit. And you can read. In fact, I will suggest something which which you should read and tell me, because there are many things in profile. I mean, I just know the definition of profinite group actually. That's about it. So I'm just telling you, just telling you the definition so far, nothing more. So this now the fact. So there are some facts which you should prove. G is a topological group and so on. It's fine, but fact is that main thing is that G is a compact, and this is just point set topology. This point set the topological group part will just be coming from topological groups, but this part is point set topology. That G is compact and totally disconnected. Okay? And it is just point set topology. Compact will come from Tychonoff's theorem, that product of compact sets is compact, and then this is a special kind of subset. So this will also be compact. It's a closed subset basically, but you can prove it first yourself. And totally disconnected, you should try to just see the definition. But yeah, we will not dwell into this. This could be one of the things to actually do. Okay. So what is next? In what should I say next? Any questions that come to mind? Maybe that will help me to think what to say next. Maybe one question is, how is this related to Galois theory? That could be because otherwise this is just this is good whatever, but it is just, yeah. So how is it related to Galois theory? So theory, profinite groups, or connection to Galois theory. Yes, just a minute. Yeah, but one problem is that kind of so far we do not have any good example. Maybe we should just have one example of a profinite group, which is not just a finite group. And then we should say just, yes, not a finite group, because finite groups, I suppose, are profinite by definition. Because you see, right, in this you can just take I equal capital I to be singleton, and then every finite group is profinite. But you would want an example which is more, which is an honest profinite group. So I can say, like, I've given an example here, but this is, I don't know if this is useful. So maybe we should use 5 minutes to just see a more concrete version of p-adic integers. Is that fine? Just, and then I will tell you to read some things and share with me. Tell me next time. Okay. Then I will try to show the connection with Galois theory. And there also there is a lot of things which I only know the statements. Yeah. So here let me talk about p-adic integers from a slightly different angle, but you will see that they are the same things. So, p-adic. Yes. So you see that we have put a topology on the p-adics. Yes, and it is just a minute. Yes. Let me go through that. Just look at the topology once again and motivate the metric. So So can you give me in, can give me an open set, an example of an open set in this topology, or closed set? I mean, it is totally disconnected, so uh, that implies, does that imply every open set is closed? Yes, right? So there should not be any difference between opens and closed in this topology, in a totally disconnected topology. I mean, I'm saying just look at Q, the rationals, right? So if you look at okay, no, I'm sorry. Yeah, maybe we will think about that later. Connected, yes, right, yeah. Yeah, let me just, because let's also, okay, let me not, otherwise it's it, yeah, yes, right. So that's totally disconnected. So like rationals, right? So so the rationals, every point is a connected component, right? And how do you prove that? Can we quickly prove that every point is a connected component? It's connected, but every point is a component, because no other subset is connected, right? So that's there. So no other set is connected, because you can just separate it. Yeah. So yeah, I mean, if you want to look at the rigorous definitions, then you should look at Pankreus or some book, and also then you can prove other facts about totally disconnected spaces. They're very interesting spaces. Yeah, contrary to what one might think in the beginning. So is it true that every set that is open is also closed? I'm just asking that for my, I mean, because it's bothering me. So U in Q be open. So is it also closed? Sorry to digress a little bit, but just to answer this question, 'cause- right. Yes, it is not closed, because if we take all rationals less than root 2, then this is an open set, but it is not closed. Or wait, sorry, yeah. Yeah, the question is whether it is closed in Q or not. It is not closed in R, of course, but is it closed in Q? Sorry, it might be closed in Q. Yes. How? Why is it closed in Q? Huh? Right. Then you, yeah, or minus infinity comma root 2. Yeah, correct. You get that. Yeah. So it is closed. So that suggests that everything. Yes, it is open by what you said. Right? It is the intersection with, yeah. But then you see U and U complement. This forms a disconnection of Q. Disconnects Q. So yeah, I mean it certainly disconnects, right? Because it's a union of components, and so if it's a disconnection, then U complement should also be open, right? That's that's yeah, that's fine, right? I mean that's in general in topology that is true. Yeah, so then it is true, right? That every so basically in a totally disconnected space, we have concluded that everything that is open is also closed. Yeah, means the open and closed subsets are same. Uh, it's still, but yeah, it's true. See, yeah, okay, fine. Let's move ahead. Yes. So now can we get a example of an open set in this? An interesting open set or any open set, non-trivial open set, or I'll just say open neighborhood of zero. Yes. Every finite subgroup should have discrete topology. Uh, yes. Vaishnavi, why is that true? Why do you think that is true? Should be true. Yeah, it is true. Yes. Because you can just think of it as a finite subgroup of this and product of discretes. Yeah. Mm. Oh, they have discrete topology. Yeah, that's something, yeah, which is true. So what will be an open neighborhood in this? So so you can use the intuition from so you can use your intuition from product topology and so on. So, so it's like you can say that the first coordinate is 1, second coordinate is 2, third coordinate is 2, and after that it is everything. Yeah, this is open. Any subset? No. Why should any subset be open? It's not discrete. Each one of them is discrete, but the product is not discrete. That's correct, right? The product is not discrete because I'll just give you, yeah, box. Yeah, that's it is not box exactly. This is not box topology. It's product topology. So here, then you know the answer, right? And basically, I use the fact that this is box, this is open, this is product topology only to construct this example. Okay. Now let us look at it from. Let us look at what numbers are there in this. Okay. Like for example, so, so if we think of a number, then that number is sort of n, and it is 2 mod p square, right? 2 mod p cube, and it is 2 mod p square. It is 1 mod p. These are the only conditions on that number, uh, right? These are the only conditions on that number, and yeah, and apart from that, it is free. Okay, so right, but then yeah, that's mm, sorry. So since I asked for that's why I got confused. Since I asked for neighborhood around zero, I should give this kind of example. Okay. So what do you understand from here? So basically, you see, whatever x is there in this, you know that the first three are 0, but after that, it is free. Okay. I should do this. Now, if I give you this one, this maybe can help to build tuition. You see, this is a smaller neighborhood, right? This is a smaller neighborhood. Okay. And similarly, you can understand, right? You will get smaller and smaller neighborhoods. So if you fix the first, if the n coordinates and let the other vary freely, you get a neighborhood. And the more you fix, the smaller your neighborhoods become, right? So this is a kind of topology. This is the kind of topology that we are looking at. Okay. So how does it, so what kind of metric would fit nicely? So you can, now I should say that you can think of this thing, you can think of this thing, means this is just you can think of it like this, and later on it turns out that if you, let's see. So if you think of a metric from here, then what is a metric? So it's kind of like I am taking all x such that distance of x, uh, means distance of x from 0 or norm of x, it becomes a normed space and everything, is less than this. Uh, right? So it's like, so if x was an integer, if x was actually an integer, if x actually belonged to z, okay, if x actually belonged to z, then it's like p to the power 4 divides it, right? Is that kind of right? Yeah. So basically, you see, so the metric that you kind of this suggests, the metric that it suggests is you take let's think of only integers and not p-adic integers. If it's only integers, then this is basically will be equal to the valuation or the order of p in x minus y. So this is a metric, and this metric, if you put this if you look at this metric, look at the topology that it induces, it will be the same topology as this, as the topology that we got by doing this. And now you can feel that they are similar, right? That it should be same. But how do you rigorously show it? Well, there's that you can. I will suggest you to read that. Okay. But the key point is to basically look at this integers. Okay. Look at this valuation metric, you could say, and then you do Cauchy completion. Okay, and that thing which you get will of course again be a, it will be a ring because you are doing Cauchy completion of a ring, so you can put a ring structure on the Cauchy completion, right? but with this metric, not the discrete metric on Z. We are putting this metric on Z, and then we are taking the Cauchy completion. That will be a metric space and a ring. So it will be a topological ring. And the topology that you get is precisely the topology on ZP. And it will be in bijection with ZP also. So everything, right? So this is the construction of p-adic. You can read from any book, for example, Katok, that's the name. Uh, Svet, I don't know. Katok has a book called p-adic integers. You can read from there. And okay, so this is the idea. Okay, it's related to many things. Okay, but we can use this to get back to profinite groups. Okay, so it's kind of a limit, right? It's kind of a limit because it's basically coming from Z. Z is a dense subset of this. The only extra things which are added are the necessary things. Okay, yeah, to just to make it complete. Because Z is complete with discrete topology, but Z is not complete with that topology, right? So yeah. And that topology is basically geometric interpretation of congruences and things like Chinese remainder theorem, Hensel lifting lemma, things like that. Putting a geometric language to talk about it. Finding a geometric language to talk about it. That's one way to think. But now coming back to, now that we can say we have, there are more examples, but in fact, for Galois theory, I should have given a different example because I don't know how that is a Galois group, how that comes from Galois theory, that particular example. But I will, let me say what, let's see what I know, and then I will ask you to. Yeah, let's. So, hmm. So basically, you see, we know the fundamental theorem of Galois theory. We would like to state the fundamental theorem of Galois theory for infinite Galois extensions. That is, you can take that as one goal. I was thinking today about how to, and this is one way to say, even though I don't know the proofs, but so ah, fundamental theorem for infinite Galois extension, and this is where this is how profinite groups can be motivated. So obviously you take an extension k over L. This is a infinite Galois extension, meaning it should be algebraic. That's one of the conditions, because otherwise you can't really do minimal polynomials and so on. It should be separable and it should be normal. And those things can be defined without finiteness. So it's there. So this is a Galois. I'm not writing much now. So this is a Galois extension. And then you look at, okay. So if this is an infinite Galois extension, then this group will also be infinite. That that should be correct, right? If it's not, then the answer is no, because like R over Q, the Galois group of that is just identity. I think Vaishnavi, that's one of the problems you did, right? So yeah, so without algebraically closed, it's obviously not true. But if it's algebraically closed, I'm sorry, then it is true. This is infinite. So now we would want a Galois correspondence. Right? We would want the correspondence. So one thing is uh, that we don't have any topology on this K and L, and I don't think we put topology. But yeah, so let's not think about that, but let's just look at this. Okay, so now you want to have subgroups. Okay, so you will take a subgroup, and that subgroup, of course, you have the fixed field. of that subgroup. And yeah, I'm just writing it for my own sake to have, if you have kg, kkj, then sorry, then you have gal k over kj, things like this. So we would want that usual correspondence. So for the usual correspondence to happen, the question is, what subgroups should we take? Because if we take all subgroups, the correspondence will fail. There will not be any correspondence. Okay, that's just a fact I'm saying. You can take Q and Q closure and see if you can verify that. I have not verified it. Okay, but I just would like to think of like maybe the automorphisms you would want to be continuous, even though I'm not able to explain that here. And then the subgroups that you get by gal k over kj, that they will be closed. So thinking about closed subgroups is the obvious sort of one of the standard, okay, that you should have want to have closed subgroups. So the question is here we want closed. So the one of the, you could say, leap in faith is, yeah, that we want to have closed subgroups. Okay, but then the question comes, what should be the topology, right? And this is the question: what topology should you put on gal k over L so that the correspondence holds? Okay, let me just check it if there is also some changes in to be made in the field. No. So they just take all subfields. There is no special fields and no special automorphisms because there is no topology on the left hand side and it doesn't, it's, yeah, anyways. Okay, here you have to do something, right? So this is where I will just mention a topology, that there is a topology which does it. Okay, and that topology, that kind of topological construction is like everywhere. It's ring theory also, it comes and so on. Completion of rings and general other things. But I'll just mention the topology and yeah, maybe Prull topology. And this will just take 2 minutes. And this actually this part might not be helpful. It's just sort of a, yeah, that that and then I will ask you to like read something so that you can I can know about those things next time. Okay, the details. Yeah. So cruel topology, but you see it's such a very nice topology there, and you can the way I'll say, you see that you can actually see that it's going to be a profinite group according to the definition we gave, but the proof might take more work. So right. So the idea is to, obviously I'm just same thing here again, K over L. So here the finite Galois theory will be used. Okay, how to get neighborhoods around, how to get the topology here, right? So the idea would be to only put a topology around the identity. Okay, so you put a topology around the identity. So how do you put? So you have to tell a system of neighborhoods, right? You have to describe a local base, right? And show that it has the properties of a local base, and then you can make a topology out of it. So how will we do it? So we are going to look at finite Galois extensions. And you can understand why we are taking finite Galois extensions. Because these finite Galois extensions are going to cover, sort of going to cover the field K. Because right, every element of K is actually in a finite Galois extension by algebraic property, right? So they will cover K, And so it's like when you come this side, so it's like you have captured all the information there, and so it's good. That's a good thing. Yeah. I just this probably very vague and not useful, but so you do this, and then you come this side, and obviously you know what to look at. There's only one thing you can look at here. It's k mod ki. And this is going to be a normal subgroup and so on, but these will be my open set. Okay, and all those sort of inverse limit things are what is making these this you know sort of nice. Okay? Like having the properties of a local base, the intersection is contained and so on. Not getting into that right now, but yeah. So this will be your local base, and using this you can put a topology on this. Okay, and if it is a finite Galois extension, then you can actually you can choose k to be ki and get identity as an open set. So then actually that's the discrete topology. When the point is an open set, then every point is open set because the topology will you get by translating. So it's good that it's an extension of that. And this is okay. So this is what I to say. Now I'll just ask you to read some things from this book. So I actually borrowed this book from the library, this Profinite Groups. Okay, but I'll just I open the book here and just tell you that you can suggest you can read this and tell next time you can tell me, because there are many things in the book. So I just want to point out a few things so that uh, you will know what to start with, and of course then the whole book is there for you to read. Yeah, so just 2 minutes and then we will stop. Oh yes, I have that book. Can you see the? Okay, does it come now? Oh, okay, okay. Mm, no, wait. That's not what I want to do. Uh, yeah, probably this is also not working. Yeah, just right. Now you can see, right? Uh, yes. Okay. Cool. Nice. So this is the book which I am suggesting you to read. Louis Ribes and Pavel Zaleski, just called Profinite Groups. But I'll just point out the part that you can start with. You can borrow it from your library or something. Read. It's up to you. Yeah. So the first, maybe you should read about this inverse and direct limits. Okay. So there are many things in this, but you can pick and read. Right. And then from profinite groups. So here, of course, they go directly into things, but so you can see this last 2.11, right? Profinite groups as Galva groups. It's actually quite understandable. Okay, they don't use all these things which they have introduced. Okay, so you can read this profinite groups as Galva groups. The last result here is the important one. They say that every profinite group is a Galva group. Okay, so that's something which I've not talked about, right? Right. So I mean, but it's like just like every finite group is a Galva group. of a finite extension. Not necessarily over Q, but otherwise you can do that. You have shown that Sn is there, so quotients are there and things like that, right? Or yeah, so but yeah, that doesn't actually prove, because you don't get everything from quotients of Sn, but yeah, it's an interesting thing. So this is something which actually will interest you, because you're reading these things. I mean, up to me, like these pullbacks, push outs, and Pontryagin dualities, probably more interesting example. But yeah, so you can read this. Yeah, I'll suggest that you start reading this after the inverse limits and work your way backwards. You may need to look at few things to go back, but not most of them will not be needed. So read this and then see what you feel, and you can also present me. Especially there are some examples there which you can look at. Okay, and about the p-adic integers, what I have told you, that also you should try to do. Okay, I mean, Vaishnavi, so you should also do the p-adic things, is very concrete, and should, because what happens after this, like what the p-adic groups is a locally compact thing, topological group. So there is something called the Haar measure, which comes. There is a measure which you can put. So you can start doing integration and calculus on that. Okay, and then actually things become very non-trivial. Okay, there is this Pontryagin duality which they only prove for profinite groups, but it's there more general. And Pontryagin duality is like very important. Okay, what is the dual of Q? So John Tate, you may have heard of. So his 1950 thesis was based on that. What is the Pontryagin dual of Q? It's actually very difficult. I do not, of course, know. Okay, it involves, like, all the algebraic number theory comes in. Okay, so it's quite interesting. Once you have the measure, Haar measure, and yeah, you can do quite interesting things. And yeah, I mean, everything here is interesting. So uh, yeah, but I would say, if I have to suggest something, then I will say that read about this Profinite Groups as Galois groups, and maybe present me next time. Whoever, both of you should read, but yeah, present me. And definitely this p-adic thing and inverse and projective limits, they are inverse limits and direct limits. That also you should see. Okay, and maybe next time, hopefully, you'll have more questions and things to present. Then I'll stop here. Is that fine? Okay. Oh, yes, yes, yeah. So just Profinite Groups by Ribes. This is like, it seems to be the canonical book in this topic. So this is written from a neutral point. It's not written from an algebraic point or number theoretic point. It's a neutral perspective, which I think is cool. Yeah. So, okay. Right. If I do, I will tell you. But mostly, I think no. Yes. Yeah. I may try to take on Saturday, but actually, so we usually take it in the morning, because the evening it gets late. I come from my college, and so, so yes, that's the thing. Okay. Yeah. So was it useful, this introduction of profinite groups? I don't know. Because actually I don't know anything about it. Okay. Even though, so profinite groups are very useful, even the things which I am doing, because we are basically looking at P groups, which order is power of P. Okay. And for that, we are trying to prove some non-trivial statement, like look at the collection of all modules over P groups. Okay. And think of every module as a function on some space. Okay. And describe that space. Yes, a module as a function, because yeah, because that's usually the module is seen as an algebraic object, but a module can also be thought of as a function on a space. What is that space? Okay, and for which category of modules should you do it? Okay, so for P groups, the problem is solved. It's a solved problem if the proof is, it requires quite a lot of language. It's not difficult. But then people have already generalized this to profinite groups. Okay, there the space is slightly enlarged. Like, suppose if they said that for finite P groups, the space is projective space. Okay, then for the, sorry, for the finite P groups, yes, is the projective space. Then for the profinite, it should be what? So there is something called the infinite projective space. Okay. Now, with the correct kind of topology, now people who have done, like, suppose I've done this algebraic topology and I know CW complexes, so I know what's the correct topology. And then actually it turns out that sort of that's the correct topology. And then you have the sort of the space on which you can think of these modules over profinite groups as functions, and that leads to a lot of things. But then when you go to infinite projective space, then topologically also a lot of interesting things about that space can come, and that people use to again improve results in module theory, and even about eventually about the profinite groups. Okay, it's a big circle, amazing circle of ideas and very active. So generalizing things to profinite groups, and even there are other concepts like stratification and so on, which is so quite interesting. Because think about it, I mean, before you take inverse limit, mathematics is kind of like combinatorics. Everything is discrete, right? Before you take limits, everything is sort of discrete. Right. Everything is just sort of counting. But once you take limits, interesting objects are constructed. And this is one such example. Right. So, I mean, finite groups are, I suppose, quite interesting. Not like that, but yeah, you enter into a potentially a very interesting place. Okay. So we will definitely meet next Sunday. And if there is something else, I will tell you. Okay. Yeah, that is also, and also obviously the question you asked about simple groups. Mm, You should, yeah, you should tell me. It's interesting, but I've never done it. Yeah. Okay. Yeah. 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 So yeah, Vaishnavi, yes. Yes, yes, in the morning. Yeah. If it is cancelled, I will tell you, but otherwise it is there. But even then, I will send you a mail. So that is also there. So yesterday you were not present, right? I Yeah. Okay. I've uploaded it. If you can see it, and if you have any questions, of course, you should ask me. Yeah. Okay. You have any questions now? Okay. Then you should think about these things. Okay. Then goodbye. Okay. Yeah. No. Thank you. Thank you. Bye.